Now that we know the basic mechanisms for substitution and elimination reactions, it is important for us to know whether a substitution product or elimination product would rather form in a reaction. So let's give some examples of this. Let's say we have a good leaving group attached to a primary carbon, such as bromoethane. And let's say we have also an unhindered strong base, such as the ethoxide ion, which is CH3, CH2, O-. So from these two reactants, we know that we can have both elimination, E2, and substitution, SN2, happen. But which one predominates? Because this carbon here is a primary carbon, it makes it fairly easy for this nucleophile to attack this carbon here. So therefore, the majority of the product we would form would be an SN2 product, being this. However, because this is a strong base, we can also have it do elimination, in which we have this act as a base, taking off one of the hydrogens from this carbon, forming this product. Ethene. Now, because it's fairly easy for this nucleophile to attack this carbon, the majority of the product would be this. So in this case, it would be about 90% SN2 and only about 10% E2. Now, this ratio changes if we use something that is a weaker base. If it is a weaker base, we should expect that elimination should happen to an even less extent, because the base would have a harder time taking off a hydrogen here. So we should expect that a ratio would be about 95% SN2 and only about 5% E2. So let's say we have, instead of having the leaving group on a primary carbon, let's have the leaving group on a secondary carbon, such as 2-bromopropane. Let's use the same nucleophile base we had before, which was the ethoxide ion. So the case changes here because we have a secondary carbon here. Because it's secondary, we have one more carbon instead of a hydrogen here, make it difficult for this nucleophile to attack this carbon. So instead of having substitution predominate, we instead have elimination happen. So what would we get? We first get propene from an E2 mechanism. We also get, to a small extent, the substitution product, which would be this. Now the ratios in this case would be about 79% from elimination and about 21% from substitution. Now let's increase it further, so instead of having the leaving group on a secondary carbon, let's have it on a tertiary carbon, such as this, and ethoxide as a nucleophile. So from earlier, we know that since this leaving group is on a tertiary carbon, instead of having SN2 be the main substitution mechanism, we instead have SN1. So basically, in this reaction, we have a fight between SN1 and E2, and which one would predominate? Well, elimination would be highly favored in this reaction, simply because you form a more stable product. So the final product you would get from elimination would be this, and you would get a little bit of substitution from this. Now the ratios are about only 9% for SN1 and 91% for elimination. So what happens if we change the temperature of a reaction? We know that elimination reactions have an overall higher activation energy than substitution reactions because more bonding changes occur in elimination. And we also know that if you increase the temperature of a reaction, you also increase the average kinetic energy of the reactants. Therefore, we should expect that as you increase the temperature, the proportion of molecules which can overcome the elimination barrier is higher than the proportion of molecules which can overcome the substitution barrier. Therefore, a general pattern results in which if we increase temperature, you also increase the percent of elimination. Now, in all these cases here, we always used a fairly unhindered base, meaning a base which can easily attack if it is possible to. However, if we change the base to something known as a hindered base, the ratios change. So let's first give two examples, one being an unhindered base and one being a hindered base. So let's first give an unhindered base, which in this case could be CH3O-. And let our carbon compound be this. Now, because this base is fairly small, it is relatively easy to attack this primary carbon here. So we should expect, like before, that the majority of our product would be a substitution product, an SN2 product. So in this case, we would get this. And this is from an SN2 mechanism. And we also get a very small amount of elimination happening, in which we get this. And this is from an E2 mechanism. In this case, we have about almost all of it being substitution, about 99%, and only a tiny amount, very little, being elimination. Now, what if we change this base here to a hindered base, meaning that instead of having 3 hydrogens attached to this carbon, we have carbons attached to this carbon. So let's give an example of this. And let's use the same carbon compound we had before. So because there are additional carbons attached to this carbon here, it's fairly large, making it difficult to attack this primary carbon here. So instead of having substitution being the predominant reaction, we have elimination happening, in which we have this act as a base and taking off a hydrogen, one of the hydrogens, from here. So the main product we get would be the E2 product, and the smaller product we would get would be the substitution product. And here, in this case, we have 85% elimination and only 15% substitution.